Hi, I'm Jungu Park from Seoul National University. I will introduce the paper HandOccNet, Occlusion Robust 3D Hand Mesh Estimation Network in CVPR 2022. This work is done with my colleagues Young-woo Go, Kyung-sik Moon, Hong-seok Choi, and my advisor Kyung-woo Lee. Star denotes the equal contribution. Specifically, the goal of this work is to perform a 3D reconstruction of the hand from a given single RGB image. Despite promising results with deep learning-based methods, occlusion occurs by an object held, eliminates the opportunity to extract hand features, and makes the task challenging. Therefore, previous methods tried to utilize interaction between object and hand to compensate for the missing hand information caused by occlusion. For example, Hayson proposed novel losses to reflect physical constraints for interacting hand and objects, and Liu proposed contextual reasoning and tried to enhance the hand representation by utilizing interaction, but fails to get better results. However, these methods need additional object annotations, which require expensive costs. Also, these methods are limited to utilizing the object information in the feature level because only annotated information is employed to acquire interaction. Overall, the presented approach operates as follows. From a single RGB image as an input, our method extracts two types of features, named the primary and secondary feature. Without using object annotation, our strategy is to divide the feature into hand and non-hand objects. The primary feature includes information that can be directly used to reconstruct the hand mesh, retaining fluent information of the hand. However, secondary feature consists of the non-hand information like object and background, which is easily discarded in the previous attention-based methods. With the process of feature injection, we inject the hand information into the required location by considering the correlation between the primary and secondary feature. We find the potential ability of the secondary feature and utilize it to obtain a richer representation for 3D hand mesh estimation. As we put primary feature into the location of the secondary feature, and secondary feature is not used again, we name the process feature injection. This is our simplified architecture. Following the conventional backbone and regressor fashion, it is comprised of additional two parts, fit and set. With the proposed component in the boxes, we have the questions written above the boxes. The answer to the given questions will be explained in turn. From the feature extracted from the FEN, we fit the features into consecutive convolution layers to obtain the necessity map. The necessity map represents the scores according to spatially varying importance, which is caused by redundant information such as object and background. With this necessity map, secondary feature and primary feature are obtained with sum to one constraint and fed into the following fit module. Fit, the key component of our HandOccNet, injects hand information into the required location. It is composed of two modules. First, the softmax-based attention module finds the most relevant information from the primary feature to the secondary feature. However, the softmax function cannot handle the actual correlation when the location is not related to the whole hand information. It is due to the property of the softmax function. To compensate for the issue, the sigmoid-based attention module attenuates the unwanted overemphasizing of features from the softmax-based attention module. Also, to inject information without using secondary feature again, we delete residual connection in fit. For details, please refer to the paper. Briefly, the sigmoid-based attention module attenuates the overemphasis of irrelevant information. For example, from the red point in the left image, multiplication between the red points of the query and all elements of the key can be shown like this. While softmax normalizes values into high correlation based on the relativity, sigmoid can filter the unwanted extraction. Different from the fit, our set enhances the injected features from the fit. As we employ a conventional transformer with an attention module and fit for module, we will skip it. Comprehensively, different from the conventional transformer like that, fit injects features, and the heterogeneous inputs are fed into the softmax-based and sigmoid-based attention modules to generate a feature rich in information about only the hand. To inject feature, we do not use self-connection in fit. In the tables, we compare our HandOccNet with state-of-the-art methods on the widely adopted dataset, HO3D and FEHA. For all metrics, ours performs favorably against the previous works, indicating a better reconstruction quality. Specifically, our proposed methods improved the accuracy by 28 and 10%, which is a significant improvement in this literature. Lastly, we compare the qualitative results with our HandOccNet and previous state-of-the-art methods. Our result provides visually pleasant output even in the severely occluded situation, which further justifies our occlusion robustness. Thank you for listening to the presentation.